there were actually two research from our team already there last time on the Beam Symposium, but it's my first time, so I will profit to show you a bit on other research we are doing in Kassel. And to start off, it's not working. No. So inspired how nature can grow or print, let's say, continuous structures and connections. This talk will explore research in additive manufacturing with timber. And also this idea of growth, I will further develop up to the integration of the actual growing processes in additive manufacturing and the corresponding materials. And what you have probably seen, actually 3D printing with timber exists already on the market, but it's usually more the materials that are made to look like wood, but not to behave like wood. So most of these processes use filaments made from wood dust and, for example, PLA or other polymers, and of course that destroys the actual cell structure and the continuous fibers you have in the material. So that reduces or changes completely how that material actually works. And we have in the past investigated alternative materials, wood materials for additive manufacturing to keep these continuous fibers. So one is willow rods. You can see on the left side, the fast-growing species grows in around 1 year, like 2 meters, so it's incredibly fast. And the other are veneer sheets that are typically used in furniture and are therefore actually aesthetic reasons. And this research on willows that has been ongoing for several years at the University of Kassel with multiple collaborative research projects and groups, and how you can make then such a continuous filament or actually yarn. These willow rods are split in slices and then further processed. The profile is standardized. We join them by slicing them and do a kind of miniature scarf joint, and then we glue them together. And then you can roll this on standard spools. It's a highly flexible material, as you can see. You can even tie a knot with this material. And this was actually from the beginning not thought for additive manufacturing, more for industrial use, for weaving machines, for example, so architectural textiles. And there were lots of studies done for that, even with integration into polymer matrices for additional strength. And then we translated this concept into robotic production and additive manufacturing with these continuous wood filaments, and filed a patent in 2019 for this process, which was granted 5 years later, 2025. And that was a first step, of course, to confirm also the technical novelty and the feasibility of using wood in a continuous manner for additive manufacturing. And you can see here the material properties in comparison on the strength, and on the top you can actually see this kind of brown color. You can see that PLA actually even gets a little bit less strength if you add the wood fibers to it. So it doesn't add to the strength. And you can see also that these willows achieve a much better performance comparable to PLA with carbon fibers. And then also these beech veneers, they're even a bit better. Also, one thing to compare, if you think about natural fibers or other types of fibers, they have actually quite a lot of energy you need to make them, so they don't perform so well. So you can see here the natural fibers, they're in between here, the CO2 equivalent, around 500 to a ton even to make one ton. Glass fibers are much higher. If you think about carbon fibers, there we would have to go 10 times more. So you have to imagine here the screen 10 times. So it's around 30 to 40,000 CO2 equivalent tons. So just as a comparison for that. So to develop this further, we actually needed a more industrial available material where we could also have large quantities, not in meters, 100 meters, but like kilometers. So we can fabricate and do fabrication experiments. So we actually went to another material which was already available. So veneer offcuts, which can be then made into veneer edge bending. So that's also for the parts you see on cheap furniture. You can have a boarding or on a table or so on with these veneer bands, and you can roll them up to 200, 300 meters, and then finger joint them, and this can be really strong, stable, flexible, and so ideal for our processes. And that's, of course, a material which calls also for highly material efficient techniques and inspired how plants achieve stability through the lignification of cell walls. We went into this idea of creating hollow construction methods, which optimized fiber arrangements through winding techniques. And these winding techniques, as you have also seen before, are previously limited more for these synthetic fibers, aerospace, and so on. And we developed then processes for that. So starting from really small dimensions in the first projects, so a tube of 4 centimeters, we scaled this up really quickly for also a project we had to realize up to like a one-to-one building system and ceiling structure. You can see that here. And this, unlike these fibers, it's a really, really thin material, so 0.5 millimeter, quite fragile during the application. And you have to imagine a bit like you try to wrap, for example, a vase with a newspaper also, and you have to do that without any wrinkles or something like that, that it doesn't break. And so in this process, it's even for robotics really hard to get this kind of precision throughout the process. And actually, we tried to wind for time reasons once one of these columns by hand, and it was simply impossible. We were not able to do that by hand. So a little film where you can see a bit. I don't think we have. Do we have some? No, we don't have noise. So I'll comment this a bit. So you see our fabrication system here. So we have large robotic lab for that, and with a mandrel around 4 meters in length, where we can do these experiments. And we are using, therefore, certified PU structural adhesives for timber. And then we develop these tools with the whole integration for that. Usually, actually, for these types of adhesives, you have to later press, hot press, to cure the adhesives. What we are doing is different, is that we are actually, during the process, we apply tension with a robot. So using the robot force and really tear it on the mold, so it's a lot of tension on it. And this is enough that actually we have the, let's say, tension goes into compression, and then it's enough to cure the adhesives for that. So this approach is, of course, much more efficient. See here a bit testing, and the application of the adhesives is in the process. The project conceived as a building system with large range of possible arrangements, of course, and in the current project follow-up, what we're doing there is actually to develop this further for building additions with especially low weight, super low weight. We have to imagine here we're talking before in presentation about centimeters, 4 centimeters, really little. This is a structural dimension of 6 millimeters. So just to give you an idea of kind of how light this is, you can easily carry a column like this, one person. And you can achieve also a range of different patterns, of course, through the winding sequence. So we're also looking at, let's say, the application of this in horizontal layer-by-layer approach, so let's say more traditional 3D printing. When you do that, that results in completely different requirements, of course, for the whole process, because there, for example, we can't apply this tension, compression, or so on. So we have used also different tools and fabrication processes for that. And also for the layup, you have geometric requirements. And we have developed through a huge amount of iterations tools for that. It's possible, you see here, to print overhangs around 35 degrees. We can even print bridges into the air, laminate that into the air. In this approach, we actually need to cut when we want to do curves. We need to cut the elements and then apply, let's say, portions of these filaments. Did some studies also to change the direction of the fiber, and then you have to lay this up. It's also interesting, but it's more for smaller scale application where it makes sense. So this process, as said, requires really fast curing adhesives, so the complete opposite what we saw before. Before we have a really long curing, so around 1 hour curing time. Here we want something which bonds initially, and we tested also large amounts of systems for that, UV curing, also gluten glue, chitosan, and so on. At the moment we're using a reactive hot melt for that, which gets this initial application possibility. And you see also here a drawing of the current setup for that. So current research on that focuses on curved and also planar and curved components, where we are using also thin wood plates as the bed for that, which we'll later use again, which stay with that as a lost formwork. And then we apply additional layers of 3D printed timber for that to get more reinforcement, and then for slab-like systems and so on, or wall systems for that. We've also done more three-dimensional printing of like 3D lattices, exploring also the bending potential of these. So let's say carving it through the process and getting a really high volume of components really fast. You can see this process here. And for that, we also explored actually a different kind of joining where we wouldn't use any more adhesives, because that's if you go more into this, let's say, biomaterials, at some point you say, you want really a 100% bio-based product. And so we looked at, it was at the time when I was actually visiting research professor at the EPF Lausanne. There was friction welding studied there, huge machines and so on, where you actually use the thermal energy, kind of putting together timber by only let's say rubbing it together, and you can activate the lignin in the wood in creating a natural bond. Since we are using these paper-thin elements, we don't need so much energy, so we went into another process, which is called ultrasonic welding. And you know this from the masks we were all wearing a couple of years ago. Those are actually done through ultrasonic welding, so it's more in the plastics industry. And you use this kind of kinetic energy into thermal energy, melting the lignin in the wood, and then this becomes actually the adhesive for that. And we were looking for these lattices were quite interesting, how to use this in architecture, and that's where mycelium comes into play. That's a material we have been using or researching in since around 5 years. It's the root network of fungi. So before the mushroom comes out, is the root network, really fast-growing material. So if you compare that to timber, you have around 35 to 70 years until you can use it. And then you have mycelium, which grows in large components around just 1 or 2 weeks. So I always say it's like the light speed for a construction material, super fast. And you can also change the growing conditions, and that changes the material properties. So quite interesting, has been really a hot material, let's say, in the past years. Has properties, really good acoustic properties, insulating properties, similar to EPS foams also, so not very strong. And you see there it has been used for lots of exhibition structures, but with very small elements and short spans, so very limited structural capacity. And that was the idea of the research, to actually combine a bit like, from reinforced concrete, 2 materials together, and create actually a reinforced mycelium through these 3D lattices. And you can see that here. So in the first step, we first fabricated these lattices, of course, and then we filled those with mycelium substrates. And then within 1 or 2 weeks of cultivation, this becomes bonded by the biogrow, so that's a bit different than with concrete. We don't just pure the concrete inside, but actually it grows inside, uses this as a lattice, and then also connects with the timber there. And what application? So that these numbers have been also shown quite a lot, but actually one thing which is not so often shown is refurbishment, especially for offices. A new company comes in, takes out all the interior walls, and this we identified as an ideal construction system for that. So drywall construction can reuse with these materials and use also the properties you can get from acoustics and so on. And mycelium is not just one material, it's actually quite large combination of materials and also substrates. We used the reishi mushroom, Ganoderma lucidium, for that because it can actually grow on timber, and it has quite a high resistance to combination. And then we are varying also the types of substrates we use for that, because you can actually achieve quite different material properties, especially for the acoustics. Here a short film for that, showing a bit how that works. So the purpose is office partition walls, and we use one material with a high density to block the sound waves, that's the sawdust, and then another material with a low density to absorb the sound, is hemp. And you can see also it's still a lot of manual things used there. We have pre-grown mycelium, which we have first to shred, and then we developed a tool method for that, which is actually trying to minimize contamination and reduce this kind of manual handling. And we developed actually a cyclone-based robotic tool where we can suck the material in and then deposit it at where we actually want it. And then you see also it's a process where these substrates, they require different growing times. First, you have the sawdust, which needs to grow longer. It's more dense, but it needs longer for the mycelium to grow through it. So it's first deposited, we let it grow, and then the second material comes in, which is the hemp. And there you can see also a bit how this tool works. So at the moment it's very coarse, but it's also a coarse material. We don't necessarily need to, use it at a millimeter precision or so on. And we also want to make large components. We're not looking at 20 centimeter component, but like a 2.5 meter component. We want to fabricate with that. And there we see again the fabrication also of these lattices. There we discovered through a lot of tests that actually the way how we make these sound waves, we can absorb different types of sound waves. The timber waves, we can absorb different types of sound waves, so low frequencies. So all that comes together in this project. And there you can see we unmolded. Now it became a really construction system with with multiple panels and so on. And at the end you see a bit, actually through these different projects, that's where different demonstrators we built. On the one on the right, one was exposed also last year in the exhibition. To conclude, wrap up, so from timber-based additive manufacturing to growth-based living materials, also an evolution, I think, from going from chemical adhesion, PU adhesives and so on, up to physical and also really biological integration. And I think that's quite interesting future purpose to try to see how these things come together and how joining and also the binding in these processes can be quite different and goes towards a more biological integrated way. And of course, in bringing the growth process into the lab, we can not only design forms which mycelium grows, but we can also design material properties in the lab and density, acoustics, and so on. These new methods can help us to develop interactive, customizable, and regenerative components. I'm over the time, so that's, of course, it's a huge team behind that, and thank you very much again for having me.
So, thank you very much for the presentation. You talked about acoustic insulation, but I was wondering, how is it about thermal insulation? Is it as fluffy as it looks like? Does it work as thermal insulator?
Yes, it can also. I mean, there are actually also companies working on exactly that for thermal insulation. There was not an idea for this project because we were really going into separation or dividing walls, so that you don't need really the thermal insulation so much. But it's actually from one of our partners from industry was the original idea that they would go really in insulating blocks.
Okay. And when talking about using such biomaterials as interiors, how about the fire security?
That's quite good actually. So it doesn't really burn much, and it works quite well. We don't have like yet these, let's say, full fire tests because that's quite quite a cost problem. But in the next projects, we will try to also do some large-scale fire tests. We have done some small-scale tests for that, and there are also some other research studies on this. And it's at least for the current uses we are expecting, it works quite well.
Alex is asking this question because he made some experiences with building with paper, and he also did these testing and say it has some kind of similarities. When I go to the next question, the things you targeted with paper, what about water? Is there any risk in dealing with water? Because otherwise you completely need to wrap it and seal it.
Yes, of course. I mean, it's a bit like any other building material. At the end, I mean, that's what's maybe something I didn't show so much. Of course, we don't let them grow, when it's already built in. We actually stop the growing process at some point. We really cut it, so that's actually through, you have to heat it up to around 60, 70 degrees, or you can also let it slowly dry. It's also a possibility. Or actually large components, we let them dry it in the sun. It's also quite effective. So there you actually kill the mushroom, let's say. And then it's very stable material. We have some components.
It's 10 years and it just smells, it's not degrading. So I think my question goes a bit into the direction of, we know it's not burning, we know it's actually water repellent, so it's actually a very exciting building material, but I know for a fact this has a very distinct smell. Do people, because now the application is office, acoustic barrier, whatever, do you have some kind of post-treatment that would, get rid of this fungi smell?
Mm-hmm. Yeah, that's a quite interesting question, and it's actually often also in the discussion about that, because it's also this kind of idea, how do you expect such a material which you don't know? I mean, for example, timber, it's quite different. We have known it for centuries, even longer, and we love how that smells. You go into a timber building, it's like, oh, this is nice. Even though it's actually sometimes not so good for you, especially in a new building. But we love it, because we are used to it, and I think there's also some idea of acceptance of these new materials for that. But one thing is also how you grow it in this process. Actually, you can make it almost without any smell. And sometimes I've seen exhibition pieces which were a little bit moldy or something, and you smell actually not the mycelium, but this really. And then it's not nice. So I think that's something. And then there are actually also studies you can, during the growth, you can put also some agents and even create a smell. So that's another interesting field to maybe get a first acceptance for people to say, oh, this is not it doesn't smell nice.
All right, one more from the audience, and then we go into our lunch break.
Have you tested the structural performance of the, let's call it the reinforced veneer mycelium panel to a normal panel without reinforcement?
Yes, of course. I mean, don't have the numbers now with me, but just maybe an extra slide for that. We have done some tests, of course, lots of tests for really 3-point bending tests and so on, but also the large components. We have tested to see actually for these walls, what you test usually is actually someone runs against it. And that's actually quite a load you need to put in there. And so we tested this also against the structural calculations from our team from Arab. And we were performing similarly, and we went up to with 5 people on that. And actually this was still, we still have it in the office. You don't even see it much where we put all these sandbags. So it works quite well.